This video is going to discuss the Wheatstone Bridge. The Wheatstone Bridge is a special circuit that was published by Sir Charles Wheatstone, and which is why he gets a lot of the credit for it. But this circuit here has 5 resistors, and so we have resistors 1, 2, 3, 4, and 5 set up kind of in a diamond. So this diamond shape is quite often the shape that we see it in, although a lot of times we also see it more in an H sort of shape here. But what's interesting about this circuit is we know we can apply mesh analysis to this circuit, and we basically we'll have 3 loops then, A, B, and C. So if we look at this circuit down here, we have a 3 ohm resistor, a 4 ohm resistor, and a 2 ohm resistor in loop A, so that gives us 9 ohms. Then we have A and B are sharing this 4 ohm resistance, so we subtract off the 4, and we see that the loop A and loop C are sharing this 2 ohm down here, R3, so we'll subtract that off. And then if we look at loop B, we have these 3 resistors, R1, R2, and R5, and so we add those and that gives us 11. And then we have to subtract the one shared between B and C, which is the -5. And then we do our C matrix, which has our resistor R5, resistor R3, and resistor R4, which gives us 8. So now when we solve this, stick this in our Octave or MATLAB program or our calculator, and we solve this, and we get our currents. IA is 4 amperes, IB is 2.6667 amperes, and IC is also 2.667 amperes, which means that if you take IB, which is defined as going over here from the right to the left, right, because it's going clockwise through this top triangle. So it's going through R5, it's going from the right to left, but IC is going left to right. So these two subtract. So if we subtract IB minus IC, we shall see that the current through the resistor R5, so that's the resistor, the current through the resistor R5, so we'll call that I5, and that is equal to 0, oops, that's a current, so that's 0 amperes. All right, so if the current is balanced, if the bridge is balanced, so we say if the bridge is balanced, then the current through the resistor R5 is equal to 0. All right? But if you look at this, notice that these resistors are not the same. R4 is 1 ohm, R3 is 2 ohms, R1 is 4 ohms, and R2 is 2 ohms. So they're not the same values, but they're the same ratios. So you see here we have R2 divided by R4 is 2 over 1, so it's a ratio of 2. But R1 over R3 is 4 divided by 2, which is of course also a ratio of 2. All right? So if we looked at the circuit, if we looked at a circuit here and said, well, okay, here's A and B, and we say that what happens if the current through the resistor R5 or the is equal to 0, what that says that the voltage VA is equal to the voltage VB. Okay? And so if we assume that we're supplying this with some voltage source E that is powering this circuit, so VA would be using the voltage divider rule and saying there's no current flowing through R5, so the voltage divider rule would give us that the voltage VA is E, whatever E is, times R3 divided by R1 plus R3, right? That's just a simple voltage divider rule. So likewise, VB is going to be R4 divided by R2 plus R4 right here. So now, if these are equal, then there would be no current flowing through this resistor. And so if we do the math here, we get the E's will cancel. So we're going to have R3 divided by R1 plus R3 is equal to R4 divided by R2 plus R4. And if we cross multiply to get the common denominator effectively, so we'll have R3 times R2 plus R3 times R4, that's this part, cross multiplied, is equal to R4 times these guys. So that gives us R4 times R1 plus R3 times R4. So now the R3 and R4 terms cancel, and we end up getting the ratio, which we actually saw up here. We end up getting this ratio that we get R2 divided by R4 is equal to R1 divided by R3. All right, or if you wanted to solve for one unknown, if you said, I know what R1, 2, and 3 is, but I don't know R4, you could say that R4 is equal to R2 times R3 divided by R1. All right, and so you can balance the bridge by using this ratio. So if you know 3 of the resistors, then you can find the resistor that will balance these out. And so it turns out that this bridge circuit is very important, because instead of simply having a resistor here like R5, so instead of us actually having this resistor R5 in here, what we basically do is put a voltmeter here. And remember, technically a voltmeter does have some resistance in there. And so we can put this voltmeter on here, and now we can measure the voltage difference between A and B. And so if the resistors do not meet this ratio, we can measure this very, very accurately, and we can determine what that resistance is. And so when you look at this, then, like I say, you can determine, if it's balanced, you can determine what the unknown resistance is. But if it's unbalanced, you can determine how far unbalanced that is. So this circuit is used greatly in sensors. So one of the most common sensors is a load cell, where we can measure force. And so we have here for R4 we put in what's called a strain gauge, which as you compress an object, that compresses the strain gauge, which is really just a fancy resistor that changes resistance as it's compressed or put under tension. And therefore we can then measure that change and determine how much force is being applied. So this is a very, very common circuit for sensors trying to measure various physical properties such as force or pressure or temperature. All right, so let's just take a look at this. Here I have the code for this top one that we just solved up here. All right, so you can see here's my R matrix, and here's my V matrix for it, and then I solved this, so I determined my current I is equal to R backslash V. This is in the Octave software. And so I build up the R matrix, I build up the V vector, and then I can determine I, and then we can determine I5, which is I2 minus I3, which, as I said over here, was of course 0. But when I do that mathematically in the Octave software, notice that I get I5 is actually 4.4409 e to the minus 16. This is what happens when you punch anything in any type of computer, whether it's your 84 or 89 Ti calculators or an actual computer. You get round off error. So this here, right, this is minus 16. So that is 0.123456789 10 11 12 13 14 15, and then a 4409. So you can see that this number is essentially 0. This is just a round off value in here. But let's see what happens now if we go back to our R matrix, and let's say that this 1 ohm resistor here, R4, so let's say this R4 resistor right up here, instead of it being 1 ohm, let's just change it by just a fraction of amount. So we'll just say it's going to be, instead of 1 ohm, it's going to be 0.95 ohms. Alright, and so now I'm going to resolve for I, and then I'm going to resolve for I5, and we find out that, wow, okay, we just changed this one resistance by 50 milliohms, and my current went from 0, all right, my current went from 0 all the way up to a full 2 amps. All right, so you can see what a huge, just this tiny little fraction of a change in this circuit, or in this resistance, gave a dramatic change in the current. The current went from effectively 0 up to a full 2 amperes. All right, so that's why this bridge circuit is so useful, because we can determine a very small change in resistance very, very accurately. So that was basically a 5% change in resistance, right? So from 1 ohm to 90 to 0.95 ohms, so that's about a 5% change in resistance, and yet I had a huge change in the current, right? The current went from 0 up to 2 amperes. So this bridge circuit is very good for measuring values, and so like I say, we use this a lot in analog sensors to determine measure various different parameters out there, whether we're measuring a resistance, pressure, or a force. All right, so it's a very handy circuit, very common circuit, and this is called the bridge circuit. Traditionally, it's been given credit for Sir Charles Wheatstone, who was the first one who at least published a paper about it. So you're going to be seeing a lot of this as you go through your various classes.